I guess it's the perfect moment to start and to welcome Chenfeng Cao from Hong Kong University today as our guest, at least as a virtual guest today. He got his bachelor in physics from the University of the Chinese Academy of Sciences in Beijing, to then do the PhD in physics at Hong Kong University with Bei Zheng. And he will today be so kind to speak to us on a topic that's kind of doubly close to our hearts. Namely, he will talk about variational learning on the one hand and quantum error correction on the other. So two topics that we like and think a lot about, but they will come together in the same talk. So thanks for coming virtually. And we're looking forward to what you have to say. So the stage is all yours.
Thank you. Let me share the screen.
By the way, before you start, maybe, can we ask questions along the way, or do you want questions at the end? What's your preferred?
Yeah, sure. You can ask questions at any time.
Wonderful. Yeah, then shoot it away. Thank you.
Thank you. Hi, everyone. Good morning. I'm Chenfeng from the Hong Kong University of Science and Technology. I met some of you at QIP last month, and I can't wait to meet you in person after graduation. Today, I'm very excited to give the group talk of quantum variational learning for quantum error correcting code. We developed a NISQ algorithm, a NISQ variational quantum algorithm for finding new quantum codes. Our paper appeared on Quantum recently. It's open access. And here are my collaborators, Chao, Zipeng, Marcus, and Bei. Currently, we're in the NISQ error, noisy intermediate scale quantum. We do not have many qubits, and all the operations are noisy. We can do algorithms like the variational quantum eigensolver, but there is no guaranteed speedup. In the long future, we hope to realize fault-tolerant quantum computation and to implement quantum algorithms with guaranteed speedup like Shaw factoring. But there is a big gap between NISQ and fault tolerance, and quantum error correction is believed to be a necessary tool to fill this gap. 2022 is a very inspiring year for quantum error correction. There have been many promising experimental demonstrations that are very promising, but in most of these experiments, the logical error rate is even higher than that of a physical qubit, which means the quantum code here is not actually very helpful. And from a theoretical perspective, one reason is that the quantum code they use are generic code, not device-tailored code, because noise models on different platforms differ a lot. So if we use channel adaptive code, it will be much more resource efficient. So in this work, we developed an algorithm called Variational QEC to find channel adaptive quantum codes with a hardware efficient encoder. Well, in case some of you are not familiar with quantum error correction, I will give a very brief introduction. The first quantum code was the Shaw code. It has 9 physical qubits and 1 logical qubit. It uses 3 qubits to correct the bit flip error and 3 qubits to correct the phase flip error. Concatenating these 2 classical codes yields the Shaw code. It has 9 physical qubits, 1 logical qubit, and distance 3. A quantum code with parameters nkd is a k-dimensional subspace of the 2 to the n-dimensional Hilbert space with distance d. And there are 2 different notations. The first notation is nkd with capital K and square brackets, parenthesis brackets, sorry. The second parameter is capital K, which means the code dimension. And another notation is the square brackets. The second parameter is lowercase k, which means the number of logical qubits. And in the following, we will use the first notation. Here is the Shaw code, and orthogonal errors map the quantum code to orthogonal subspaces. If the map is injective, we say the code is non-degenerate. Otherwise, we say the code is degenerate. And for the shortcode, since Z1, Z2, Z3 errors map the code space to the same subspace, so the shortcode is a degenerate code. Degeneracy is apparently a quantum property because in classical error correction, different errors always have different effects. And any linear combinations of these errors can also be corrected. Here is a Venn diagram of quantum error correcting codes. All quantum code, a large class called code word stabilized quantum codes, and then stabilizer codes. Stabilizer codes is actually a measure zero subset of all quantum codes, but most research are focusing on stabilizer codes because analyzing quantum error correction under the Pauli framework is relatively realistic and easy. Then the CSS code and quantum low density parity check codes. The well-studied Tori code belongs to all classes. Each quantum code is a k-dimensional subspace. And in 1997, Neal and Laflamme proposed a sufficient and necessary condition for quantum error correction. It says that a quantum code with orthogonal basis states Ψj can correct the error set E alpha if and only if the equation Psi E alpha dagger E beta Ψj equals lambda alpha beta delta Ij holds for all errors and basis states. This is a sufficient and necessary condition that tells us whether a quantum code can correct some errors. And why do we care about the distance of a quantum code? The distance d of a quantum code is defined by the largest possible integer, such that Psi O alpha Ψj equals lambda alpha delta Ij holds for all Pauli tensor products with weight smaller than d. So comparing the two items, we know that distance d quantum code can correct arbitrary error sets, with each error non-trivially acting on at most d-1/2 qubits. And in quantum computation, errors are usually local errors. So the distance is an important measure. And here comes our algorithm. First, we initialize k orthogonal input states. They are computational basis states. So they are product states that is very easy to prepare in a lab. Then we apply a parameterized quantum circuit to these states. The output states are still orthogonal because it's a unitary transformation. And the output states, denoted by Psi1 to Psi span a quantum code. It's a parameterized quantum code. The main philosophy in our algorithm is we update the circuit parameters theta to find the quantum code we want. And even if we randomly sample theta, the output is a random quantum code and it can be useful sometimes.
I'm sorry, can I ask a very stupid question?
Yeah, please.
So, I mean, a code is, of course, a subspace, right? Like a linear subspace, right? And I mean, how do you necessarily generate a subspace in that fashion? I mean, are you thinking about, how do you do that?
I do not generate the space. I just generate the basis states of that space.
I see.
Because
okay, then another question, like how do you make sure that these basis states are orthogonal? You don't, right? You just look at linearly independent vectors that then span a space. Is that so? You're not.
Oh no, because the input states are orthogonal. Then after the same unitary.
Good.
Yeah, they're still orthogonal.
I see. You have an input space. Very good. Mm-hmm. Yeah.
Thanks. Then, if we want to find a channel adaptive quantum pose, we need to define some cost functions. Here we define two cost functions. One is the L2 norm cost function, and one is the L1 norm cost function. They are devised according to the Neal-Laflamme conditions we discussed just now. They equal 0 if and only if the Neal-Laflamme conditions are exactly satisfied. But we have two cost functions here because the L2 norm cost function is very friendly for optimization. The gradients are continuous. But the L1 norm cost function, we will prove that is directly related to the code inaccuracy. That's why we have two different cost functions. And if we want to find a channel adaptive quant code, we set mu in the cost function as E alpha dagger E beta. Here, E alpha and E beta are cross operators of the target noise channel. Yeah, and if we want to find a quant code with fixed code parameters like NKD, we set mu equals Pauli tensor product O alpha with weight smaller than D. The cost function depends on our task. In such continuous numerical optimization, maybe we can minimize the cost function to a very small value, like 10 to minus 10, but it's sometimes unlikely for us to obtain exact zero. We cannot minimize the cost function to zero, exact zero. But this is not a big problem because even if we use an exact quant code in experiments, the encoding circuit is not exact. So the actual quant code we use are always approximate code, and approximate code is enough. Here we proved that as long as we minimize the cost function CL1 to a very small value, then the code inaccuracy epsilon is bounded by k times square root of 2 times CL1. And which means if CL1 is very small, is very close to zero, then the code inaccuracy epsilon is close to zero, and the recovering fidelity will be close to 1. Since we use NISQ machines to find quant codes, and NISQ machines do not have too many qubits, so the quant code we found are relatively small codes. Then we can use quant code concatenation to form a large code from small codes. We have one inner code that acts directly on the physical layer. Then we have multi-layers of outer codes. The concatenated quant code has a large code length and a very large distance. In our calculation, we assume that the hardware has certain connectivity. And then we divide the hardware efficient circuit according to the connectivity. That is, we just apply 2 qubit gates to adjacent qubits. And we have multiple layers in the circuit. With the increase of L is the number of layers, the circuit is becoming more and more powerful. It can prepare more and more quant codes. But we don't need too many layers. As long as the circuit capacity has a non-zero overlap with the solution set, that is enough. We find an eligible quant code.
And can I ask you a question?
Yeah, please.
I haven't been following everything. So the top left is like your connectivity graph, I guess?
Yes.
And then, so on Q0 and Q1, you have physical qubits you want to encode?
Yeah, that's right. The
okay.
input computational basis, that's.
Okay, but then
the local information spread to the whole system.
Here it looks like then you have 5 qubits encoding 2 logical qubits.
Yeah, but the distance might not be 3.
I see, okay.
Yeah.
Okay, thank you.
Thank you. The one thing is, if we have enough layers, the circuit will be over-parameterized, which means the circuit can prepare an arbitrary quant code with parameters n and k. And when the circuit is over-parameterized, all output quant codes form a well-studied manifold called the Grassmanni. The dimension of the Grassmanni is k times 2 to the n minus k. That is, we need at least k times 2 to the n minus k independent parameters in our circuit to over-parameterize the encoder. And one tool we use to quantify the capacity of the circuit is the quantification information matrix. We define a pretty special quantification information matrix here, and the matrix is denoted by F. The parameters theta are randomly sampled, and then the rank of F equals the dimension of the manifold of all possible quantum codes encoded. Here are some numerical results that we fix n equals 7, and for k equals 1 to 4. We can see that the rank of F increases first with L and then becomes a constant after the point of over-parameterization. Here L is the number of layers.
Sorry, could you explain the different terms in this equation? Or yeah, I don't know what quantum Fisher information is, like what this calculates, a rough intuition.
The quantum Fisher information matrix for a single input state is intuitive, but this equation is not very intuitive.
We have also Johannes in the call, right? The grandmaster of Fisher information. But you might want to comment on this. But
I could.
Yeah, but let me ask my question first. And then, like, why is that so sharp? I mean, it seems like there's an upper bound, right? I can believe that there's an upper bound depending on k that's then saturated, but it's really a hard hard transition. Why is that?
Yeah, because it's sharp that at first, if we add the number of layers, there will be linearly more independent parameters in the circuit.
Okay, yeah. I think I get it.
Yeah, it's almost linear.
Good. Yeah.
Then after over-parameterization, it's a constant.
Fine. Yeah.
And short comment. I mean, on this intuition behind the Fisher information. Basically, what you do is you have a point in your parameter space. You know, you have this parameter theta here. And then you say, if I wiggle my parameter theta, how much is the quantum state going to change? So this is like essentially quantified by the Fisher information. So if it's large, or let's say like it is large in one direction, which is like one eigenvector of the Fisher information, so to say, then the state changes a lot in that direction. And then if it's small, it doesn't change a lot. Obviously, if the Fisher information is 0, it doesn't change at all. So this means you cannot go in that direction in parameter space. So the rank of this Fisher information matrix means in how many directions in the actual quantum state space can you go when wiggling the parameters of your parameterized quantum state. So that's why it's kind of, in a sense, a measure of expressivity.
Mm-hmm. Okay. So
yeah, that's correct.
Somehow we want high Fisher information so that we can get that we span all quantum error correction codes.
Yeah.
Mm-hmm. Okay, thank you.
Yeah.
Okay, in our optimization, sometimes if there are too many cross operators, we will use mini-batch gradient descent. Mini-batch learning is a trick widely used in classical machine learning that in the optimization, in each iteration, we do not need to use all the data. We just need to sample some cross operators to do one step of gradient descent. Then we do mini-batch learning with the L2 norm and eventually fine-tune the parameters with the L1 cost. Okay, here comes some numerical results. First, we apply our algorithm to find quantum codes with fixed parameters, NKD. The figure here shows the cost function we obtain. The white boxes indicates that we successfully minimize the cost function to almost 0. It's smaller than 10 to minus 6. And the blue boxes means we failed to minimize the cost function to 0. There's a clear boundary between achievable and non-achievable quantum codes. We successfully found many known and unknown quantum codes. For example, we find the code with parameters 523. That is a unique code. It's called the perfect code. We can use 5 physical qubits to encode 1 logical qubit and to correct arbitrary single qubit error. Then we also found quantum codes with parameters 623 and 723. They're now locally equivalent to any known quantum codes. They're not even locally equivalent to any stabilizer codes. Although they have the same parameters, many different codes can have the same parameters.
Can you say this again? So they're not some locally equivalent to a stabilizer code? How would you know? I mean, how would you check?
Yeah, one tool is we can calculate the weighting numerators of these codes. And for stabilizer codes, the weighting numerators are always integers.
Of course.
Yeah.
Where's the
some codes are not.
Could we ask a question? So on the in the bottom for n equals 12, it implies this plot implies that you found codes for every value of k, which would mean that you have a subspace of 2 to the size 2 to the 7. Does that correspond to 2.5 qubits, 2.5 logical qubits, or what does that mean in terms of the code that you found?
Then it's qubit. It's now a qubit system from the logical perspective.
And what's your input state then? Sorry.
We just input k orthogonal input states to.
Okay.
So the k can be 5, 6, something.
Cool.
Thank you. And as I mentioned just now, that at length the circuit capacity has a non-zero overlap with the solutions. We can find an elliptical code. And here, in all the calculations, actually, I just used the number of layers L equals 3. We can already find an elliptical code. We don't need a very deep circuit. And there's an open problem in this field is whether or not a quantum code with parameters 733 exists. Can we encode one qubit with 7 physical qubits? And according to our numerical results, we believe such a quantum code does not exist because we use an over-parameterized quantum circuit and sampled over 20,000 initial points. We still cannot find it. But this is just an evidence, not proof.
Because you could still get stuck in local optima also.
Yeah, that's possible. Then here are some learning curves. If the code parameters are compatible, for example, there exists a quantum code with 623, 523, the cost function can be minimized to 0 very fast. And they're unlikely to get stuck at a local minimum. But if the code parameters are incompatible, for example, if we try to find a quantum code with parameters 423, that's not possible. Then the cost function will get stuck at a very large value.
Can I ask a stupid question? I mean, of course, that's all run on classical software, right? Like simulating the quantum software. So at the end of the day, it's like some kind of tensor network that you're constructing in one way or the other, right? And this will have loops. And we know that the contraction complexity of a tensor network would grow with the tree width of the respective graph that captures the tensor network. So have you thought about the scaling of the classical contraction complexity for the settings you look at? I mean, just treating this as a classical way of getting new codes. I mean, forget about the quantum narrative. At the end of the day, it's just some algorithm that generates codes, right? Which is absolutely beautiful.
Yeah.
So it makes sense to ask like what the contraction complexity is now. It scales with the system size. Have you thought about this, or is this a pointless question?
Yeah, we did not think too much about contraction complexity, but we do try the matrix product space, and MPS does now perform quite well. Maybe it's one-dimensional, and code with good properties are usually high-dimensional, the entanglement. Yeah, but I think it's worth thinking about. for the classical part. Okay, I will move on. And that numerical result is for quant code with fixed parameters. And then we try to find quant codes for a given noise channel to find channel adaptive quant codes. The noise channel we consider here is arbitrary single cubed error, as well as adjacent ZZ errors. For graphs A to H, we find quant codes to correct arbitrary single cubed error and ZZ errors on adjacent qubits. And some of our codes are locally equivalent to a stabilizer codes. And we can even find its stabilizers. But it's pretty hard to verify whether two quant codes are locally equivalent. We have to use a stupid brute force method. Here is a comparison between one of our code and the Sting code. When there only exist single cubed errors in one, both our code and the Sting code can correct the error and improve the fidelity. But if the system also have adjacent ZZ errors in two, then our code still works, but the Sting code does not work anymore. But this is not a fair comparison because the Sting code was not designed to correct collective ZZ errors. One big challenge for variational quant algorithms is the Barren plateaus phenomenon. When the parameterized quantum circuit forms a unitary to design, then the gradient decays exponentially with the system size. Previous research indicates that if the cost function is local and the circuit depth is about a log n, then we can avoid Barren plateaus. The circuit is trainable. Otherwise, the circuit is not trainable. And we observe the same phenomenon in our numerical calculation. We try to fix the circuit depth L equals a constant or equals log n. In such cases, the gradient does not decay. However, if we fix L equals n, the gradient decays exponentially. And in quantum error correction, because usually errors are local, and we just care about quantum codes with a very shallow encoding circuit. So Barren plateaus is not a big challenge for our algorithm. And finally, we did a toy experiment on a 5-qubit IBM machine. We used 4 qubits of the machine to find a quantum code to correct the amplitude damping errors. A0 and A1 are crossover operators of the amplitude damping channel. We ignore all the high order terms and just keep the low order terms. This is our stupid toy variational quantum circuit with just one parameter. And then we compile it to a hardware efficient circuit because some qubits are now connected. And in such a toy experiment, it really works. We can minimize the cost function to a very small value, and the machine finds the correct parameter that is half pi. And in the future, we hope if we have access to some large machines, we might find more interesting quantum codes. Thanks for your attention, and please tell me if you have any questions.
Yeah, thanks for this wonderful talk. Thanks so much.
Thank you.
Questions along the way? Maybe there's more. Maybe I start with a question, which it's a nice variational algorithm, but as I said, you can also see this as a classical tensor network to kind of variationally find codes. is there a scope or hope of finding like maybe slightly less sophisticated encoding schemes, but which have the property that they're efficiently contractible, so that you can, or more efficient or reasonably contractible, so that you can go to pretty large system sizes with classical methods? Have you thought about this? Like to engineer your circuits not so much to be good in terms of expressivity as quantum circuits, but to make a good compromise in expressivity and contraction complexity. Is that something you have thought about, or is there a point in that, or?
Yeah, we did not think about it, but I agree it's a very promising direction. Yeah, I think there is the hope. There is no evidence it's not possible.
Mm-hmm.
Yeah, but maybe experiments is required to verify it.
Mm-hmm. Are there other questions?
Yeah, I wanted to ask, I mean, what do you think is like the future work to be done in this direction? Or do you think this is like a scalable approach to learn about error correction? Or I mean, what do you have in mind for the future with this?
Yeah, I think it's a scalable approach, and in the future, because we just cared about encoding in the project, and in the future, we also want to find a good way to find a decoding scheme for the codes we found. Yeah, sometimes even if we know the code can correct the errors, we don't know how it corrects the errors in an efficient way.
So are you saying that you want to find a variational quantum algorithm for decoding?
Yes, exactly.
Okay. That's interesting.
Hi, can I ask a question?
Sure.
Oh, please.
Thank you for sharing your nice ideas. So maybe I comment a bit and you say if I understood it correctly. So the cool thing about this is that you can use a quantum computer to find quantum codes, right? The use case is not that you use tensor networks to simulate the thing, but eventually you go to really big systems with a quantum, like, I don't know, 20 years in the future.
Yeah,
and you
right.
find them, yeah. And sorry. So the use case is this, am I right? You can only do, the use case is memory, right? You encode the circuit, your qubits, and then you keep them for some time and later you retrieve them, because there's no way of doing logical gates or like stabilizer measurements, for example, to correct the errors while the data is still encoded. So is this the use case that you anticipate?
Well, first it can be used for sending information through a noisy channel.
Yeah.
And then, yeah, that's a problem, how to do logical operations. And yeah, that's a problem. You're right. We do not know how to do logical gates for set codes.
But then maybe the best way to compare the performance is against dynamical decoupling techniques or something like that. And can you show the last slide with the
Do you mean the experiments?
Yeah, that was a bit fast. Did you run the experiment on hardware?
Yes, it's a very simple experiment, and we need to submit the circuit many times and estimate the gradient.
But these are data points. That's not classical computer simulation. That's quantum data, right?
Yeah, purely quantum. We use parameter shift rule, something similar to the parameter shift rule to estimate the gradient. And with about 25 iterations, we can find the correct parameter.
And did you try to do this also with phase flips, which is also an important error mechanism? I mean, amplitude damping is very important, and dephasing as well, right? So
yeah, we just did this experiment. It's very time consuming because there is always a long queue.
Yeah, and the circuit that you picked looks weird to me. So why did you not pick another one where you don't need swaps? Was it important that you start with the other connectivity, with the other architecture? Right, you pick some arbitrary architecture and then you compile it, and now you have something very deep. But you could have just picked an architecture where you don't need to swap.
Yeah, because previously we already know how to encode the quantum code for amplitude damping.
I see.
And we just want to insert one parameter here.
Yeah.
So we need some prior information.
Can you show me the circuit again, the uncompiled one? Just one slide back.
This one?
Yeah, that one.
Yeah, with just 4 signal gates.
I see. Okay, good. That's not so easy. Okay, so you picked this because there is some code that you knew you would be able to find, and
yeah.
And then the cost function. Okay. I'm surprised how well this worked.
Regarding phase errors, you will need the other encoding, no? Or because this is more tailored to correct the.
I don't see this, but yeah. Apparently.
Yeah, interesting.
One thing
Thanks.
I found it really interesting about the results you showed is it seems like all the codes, whatever setting you ran your optimization on, it seemed like either you get a very good code or you get something that's bad. Is that some behavior that you consistently saw in these small scale experiments? Is it true that basically you would never expect to get a pretty good approximate error correcting code without there actually being a very good one or a perfect one, an exact code very close to it? Is that something that's consistent with what you observed?
Yeah, in that numerical result for finding quantum code with fixed parameters, the boundary is very clear. You're right. We do not have some code with a small but not very small cost function. That's a good thing. And we also know it exists or not. And if we fail, the cost function is always larger than 1. Yeah, but I'm not sure whether.
Can you show the cost function again? I wonder how many terms there are. Oh, that's important for post-processing. Is there
here many terms, summation of
but can you even evaluate this cost function if you have 100 physical qubits?
Yeah, you're right. We discussed how to evaluate the cost function with a real hardware. If emu are not unitary or Hermitian, sometimes we need to add ancillary qubits, but they can always be estimated.
No, I wonder if you gather the data, how do you sum up all these terms? If you have exponentially many capital K, for example, you need to sum over, right? You have K squared terms where K is
log something.
No, K is the dimension of the space of the physical of the logical qubits.
You're right. We cannot have exponential K here.
Okay, I see.
So it would be interesting maybe to find a cost function that has fewer terms but achieves a similar goal.
Sure.
But now you see why this is so big, because it has so many terms.
Yeah, I agree with you, but
well,
I'm not sure whether it's possible.
So maybe I can ask the question kind of also kind of in a different way. So the epsilon that you showed, you had the slide on the approximate quantum error correction, right? So the epsilon that you had there, I guess, is that some worst case entanglement fidelity or infidelity of the code? How is that epsilon, and what metric is that epsilon defined?
Epsilon here. Epsilon is the entanglement fidelity. One minus epsilon is the entanglement fidelity.
Right. So for that's being like if you apply your state onto a maximally mixed state, or are you looking at the worst case of all possible inputs of the, you're looking at the fidelity of the channel with respect to the identity channel, because you want to ideally have an identity channel on the logical space. And I guess you can ask, what's the fidelity of the output of a maximally entangled state or the output of any arbitrary state? So did you have that maximization over the input? Out of curiosity.
It should be optimized to all possible input states with a reference system. Yeah.
Right,
So
exactly.
maybe the maximally entangled, but maybe not.
Right. Oh, okay, I see. And in this upper bound, sorry, I missed the K. I see. So this, you do have that dimensional factor between this epsilon and the cost function.
Yeah,
so should I not be worried by that? This might give you a very, this might give you a bad bound on the epsilon if you have a low cost function, right?
Yeah, from this perspective, there do exist some problems for scalability. Yeah, that's right.
I see.
If we have a very large K, we need to minimize CL1 to a smaller value.
Okay.
I see.
Yeah, that makes sense. Yeah, thanks.
Thanks.
But this is not an in-principle problem, right? It's just like it's a more demanding requirement depending on large K. Yeah, I understand.
Well, where the problem might come up is that if you want to find a good approximate quantum error correcting code in the fidelity metric, you still want to use a cost function that you can compute in an interesting way on the quantum computer, which is not the fidelity, I guess, but which is something more like what you wrote down with the cost functions that you chose. Well, there might be a gap between the actual cost function that you're interested in if you want approximate error correcting codes, which is like the fidelity, and the actual cost function that you can compute. But if you're in the situation which seems to be the case in your results, maybe the conclusion is that you shouldn't worry about this because if you get a very small epsilon, then there's anyway a very good code, an exact quantum code that will do the job. So you don't have to worry about the exact value of this epsilon, but rather the fact that it can go to some very small values, and that will tell you that there's an exact code there anyways. So I think that's already something very interesting.
Yeah, you're right. But if we know it's very close to an exact code, how to find that exact code? We're not sure about that.
Well,
Yeah, but you're right. I totally agree.
So I just have a small question. So during this process, did you discover any codes that is not known before, or you're mostly checking existing codes and manage the existing codes?
Oh, we did not find codes with, for example, we did not find codes with new parameters, but
No, I'm asking, did you find any code families that does not discovered before?
Yeah, some code we found with parameters 6 to 3 are not locally equivalent to any known codes. They're new families.
Oh, I see. That is very impressive.
Yeah.
But it's interesting because most codes seem to be qubit stabilizer codes, right?
Yeah.
Well, why? Because you can, as you have explained, you can check that. But why is that? I mean, that's kind of funny, no? I mean, there's no bias towards such codes in a way. Do you have an interpretation of this?
What is the error model? That might be important here.
Oh, here we consider standard Pauli errors.
Well, maybe that's the reason.
I see. So it's the Pauli error. Yeah, that could be the Pauli errors kind of. Yeah. Okay. Still.
Yeah. So if sorry, another related question. So if I remember correctly, deciding whether two codes are equivalent. So first of all, what does that mean? Does that mean like up to local unitaries?
Yes.
And how do you check that?
First we calculate their weight numerators. If they have different weight numerators, apparently they're not equivalent.
Wait.
That's the point, because you couldn't check. I mean, there's this famous LU-LC question, right? Whether checking the orbit under local Cliffords is the same as under local unitaries for stabilizer states. I mean, that.
Wait. I have a question. What are weight enumerators for non-stabilizer codes?
Oh, some random numbers, not integer. We cannot find.
But how do you do? I mean, for stabilizer codes, you count the stabilizers in the stabilizer group, which have a certain weight. But what is it for non-stabilizer codes?
Well, the definition is the same. We still calculate their expectation values on the Pauli stabilizers. Yeah, but the resulting quantity is a non-integer.
How do you do this for a code? Sorry, this is like
numerically.
maybe you don't have the. No, I mean, what is the equation? I don't know the equation. I literally count the stabilizers and don't compute expectation values when I work with codes. For single states, yes, but for codes.
May I share the screen for the paper?
We still see the PowerPoint slide only.
Please wait a minute.
Thank you. Now we see the Slack channel and everything.
Okay, here is the definition of weighting numerators here.
Yes.
A and B.
Yes.
We want to calculate the coefficients, AJ and BJ. Then we just calculate them according to.
So what is PC? What is PC here?
Oh,
the
PC
projector
is
to the
projector. Right.
Aha.
Projector.
And O is Pauli's.
Yeah,
with weight
Pauli's.
alpha.
Yeah.
Okay, you take the projector instead of the state. Okay. Cool. Okay, so you first check the projectors and then you have some candidates and then you maybe brute force minimize the cost function where you have like the states and you vary over the unitaries until you find zero.
Yeah. And we need to consider all the permutations.
Oh my God.
What are the smallest codes you find which are not stabilizer codes?
Oh yeah,
code with,
these are not integers.
6.
6, I see.
Yeah, n equals 6 because n equals 5, the 5 to 3 code is unique.
Yeah, of course. Yeah. I see. Then that's a good indication that that Daniel has a point on there. That might come from the error model, and then for smaller codes, there's no way anyway. And then okay, that's.
What about how do you find out it's not a stabilizer code? Is it when these weight enumerators are not integers, or will they always be integers? So I know, no, right? No, this is not true. For non-stabilizers, you see, these are not integers.
Sometimes we find very weird coefficients.
Yeah. So this is something that you can tell it's not a stabilizer code because your weight enumerators are not integers.
Yeah.
Okay. Cool. Can you still compute? No. Okay. I was wondering because for stabilizer codes, you can use the weight enumerators to compute the distance. Right, because if you know A, you get B, and then you check what is the highest value of the coefficient where they smallest value where they disagree, and that's the distance. But this is not. No, this is not how it works here, does it? What's the distance of this code 6.5?
Well, I think the distance cannot be determined.
It's at least 2, right? Because the coefficients of z in front of z to the 1 is 0 for both.
Yeah, at least 2.
Okay. Cool.
Okay. Thanks.
Thanks. That's interesting.
Thank you.
Cool. Yeah, that's clever. Yeah.
Yeah, it seems we find a continuous line between the discrete code.
Very timely. Yeah. Okay, so at the moment, it's a really nice tool to find non-stabilizer codes. And then also tensor network contraction, everything Jens says makes sense. But and that's like one thing we can do now. And the other thing is going to really large codes in the future with quantum error correcting, with real quantum computers. But for this, you need to find a more efficient code function which achieves the same job. So yeah.
But one could anyway think of like concatenation, right? That you use this machinery to get the lowest level encoding done, and then you would concatenate this with like a toric code or something.
Yes, but then you don't need the quantum computer in any stage of the determination of that. Yeah,
that's right.
But I want this. So, and is it impossible to change such cost functions to do something efficient, or?
Yeah, that's worth thinking about.
And I mean, there was another sum over the errors. How many errors are there?
But some of the states are expectation values, so there are quantum algorithms to.
Yes, but if you have to collect an exponential number of them and then sum them up, you have a problem.
I think that's not, because you can write that as sum as, I mean, with a quantum computer and all that, but expressions of the form sum over states is like a set-joint algorithm and start to invert matrices. What you get is not the inverse matrix, but expectation values taken on the inverse matrix. So those, I think that's not the problem.
So what
long-term
happens when you want to calculate this cost function?
If you zoom in over.
So what happens to calculate this cost function if you randomly sampled some errors instead of exhaustively looking at all possible errors? Is that, if you're, I mean, I would imagine that if your circuit is simple enough, so maybe of course if you're looking at all possible codes, that's going to be different. But like if your circuit and your encoding is simple enough, somehow you could hope that the way in which you're sampling the errors for which you're going to calculate, you're going to estimate some average over all possible errors. You could hope that this would not interfere too much with the way that your circuit encodes information. Would that be completely misguided?
Sorry, could you repeat the question again? I missed something.
Well, I mean, it's a very naive question. Maybe you had a sum over all errors, right? Pretty much in your cost function. What if I think of this as some big sum? You could imagine doing some type of Monte Carlo estimation to estimate that sum. If you can think of it as an average, right? Average over errors. You could try to calculate that average with some type of Monte Carlo situation where you just sample terms from that average and hope that you get something that's close to the right answer. Would that make sense?
Yeah, I think that makes sense, but it's somewhat similar to what we do with mini batch learning.
With what, sorry?
Mini batch learning, we just do the optimization with a very small batch in each iteration.
Oh, I missed that. Yeah, sorry. Yeah, thanks. That makes sense.
Yeah.
Can I point out the good comment of Jose just 2 minutes ago? I think that's really a good idea to like in the long term to make this use like these two routes. One is like with simulating the stuff and the other one quantum computers. So on quantum computers, you can maybe evaluate the cost function efficiently despite there are exponentially many terms if you have like some extra overhead on the side of the quantum computer. So there might be quantum algorithms that help you evaluate the cost function. I think that's cool in the very long term.
Really cool. By the way, if we use a symmetric circuit, I believe we can reduce the number of terms.
Yeah, I guess. Okay, what about logical gates?
Yeah, tough.
Can you do a variational algorithm for logical gates?
Well, I think it's possible. Yeah, at least we have some trivial methods.
It sounds easier to me than finding a decoding algorithm variational.
What about for existing quantum codes? Say, because this is still a big open problem in quantum QEC codes in particular.
Yeah, with quantum computers.
Yeah, how do you compile the logical gates? Because I mean, with something like service code, you already have, like, once you figured out how to do lattice surgery between two logical qubits, the problem's basically solved. But if you have a quantum QEC code with many logical qubits, say 100, then you have 100 choose 2 logical CNOTs to compile. And yeah, there have been a number of proposals to compile these gates, but none of them are particularly satisfactory. So perhaps using a variational methods might be fruitful.
On quantum hardware or on classical hardware? No. Yeah, with tensor networks on classical hardware?
No, either, I guess.
Yeah.
But just, finding some way of compiling fault-tolerant versions of these gates for arbitrary LDC codes is, something that's yet to be solved.
I mean, if this biases towards stabilizer states, you'll probably get a Clifford sequence anyway.
Okay, yeah.
You just tune the thing and run to the next clipboard and check the result. Could work, yeah. Yeah, I like the idea. That could work.
Yeah,
That's how it works. That's new. We need your more bachelor students.
It's a good idea. Indeed. Wonderful. Yeah, wonderful. Great discussion. So we have been discussing for as long as the talk went. Very good. So, is there any final comments, questions? Already good ideas coming out of this. This is great, and also the talk was great. Obviously very stimulating. Yeah. So if that's not the case, then let's thank the speaker again for this great talk, and to everybody in the audience for the many comments, questions, and ideas. That was really fun and great. So see you around, and good lunch in a second. So thanks for coming, and thanks for giving this nice talk. Goodbye.